Okay, just as a summary of week 4's things, I thought I'd do one example problem where we look at the chain rule with partial derivatives. So some of the things that we've looked at this week have mainly been the concept of partial derivatives, also applications of the chain rule. So since the chain rule we use partial derivatives to get there, I thought I'd do that. So in this question we want to find the z, actually it's going to be, to z, to t, to z to t, let's find the z to t. And using the partial derivatives. And the reason why I specify using partial derivatives is because one thing we could actually do usually is just substitute t, our values of x and y, into this function, make it an explicit function z of t, which would then just be a single variable, and do it in that way. But for the moment, let's use these partial derivatives. So firstly, remember, let's look at this function here. And I firstly want to come up with my partial derivatives fx, or which is also equal partial derivative of z with respect to x. So I'm going to use these curly d's to denote, to distinguish between an actual derivative and just a partial derivative. So here we just treat y and all the terms with y in them as if y were a constant. So here we're going to have 3xy squared becomes 3y squared with respect to x. X to the half just gives me 1 on root x, 1 on 2 root x. And then minus 2y is just treated as a constant, and so it vanishes for the partial derivative with respect to x. For partial derivative with respect to y, here we take the 2 out and we're going to have 6xy. So again, x is just treated as a constant. Here the x will vanish, and then here we just get minus 2. So they're our two partial derivatives. And now, so remember, for the z to t, we get, or what we're going to look for, the z to t is equal to the partial derivative to z dx times dx to t. So in other words, we're looking for the partial change in this function z as x increases, and then we add together the partial derivative, sorry, these are partials, the y times the y with respect to t. So for these, note that we still require this dx to t and this dy to t terms. Okay, so let's write down the information of those that we need. So I need dx to t, which from here I can see that dx to t, now these are complete derivatives because x is an explicit function of t, so this is going to be 2t. And then dy to t here is going to be the derivative of log of t, which is 1 on t. Okay, so now going back into these functions, I've just got the z dx, which is here, multiplied by dx to t, which is here, and then the z dy, which is here, multiplied by dy to t. So I'm going to put those in. So I have the z to t is equal to, so remember we've got the partial derivative to z dx, so that's 3y squared plus 1 on 2 root x, multiplied by dx to t, which is 2t, and then plus my derivative with respect to y, so 6xy minus 2, multiplied by my derivative with respect of t, derivative dy dt, so that's just over t here, and that's my expression. So I could, in some cases, do a little bit of neatening up, so perhaps putting over a common derivative or whatnot, but for the moment I think that's okay. If we wanted to get rid of the t's, we could do some transposing and express t in terms of x or whatnot, but for the moment, often we're asked to evaluate things for a given value of t. So here we could say, look at what happens when t equals 1. And then, of course, then we have x therefore is equal to 1, y therefore is equal to 0, and we can make our substitutions there as we needed to. Important things, I guess, to consider are ensuring that the derivatives exist where we're looking for them, making sure that the function exists. So for instance here t is not going to be defined for negative values or for 0, so t equals 0 is not applicable in this case. But yeah, okay.